You can see red bars are at the top, and there's mostly red and blue bars in here. If we then move on to our other two metrics, we can see quite different colors. The timing of peak, the rate of peak to no flow, the most influential predictor is the wetland area in the contributing watershed. So shout out to the Odom Center for Wetlands there. You're number one on that one. And as we kind of move down that list, we see primarily a mix of land and water use variables and physiographic variables, with only one climatic variable showing up in there. On the opposite end of the spectrum, if we look at then the timing of no flow within the year, we can see that one is dominated by climatic conditions. Specifically, just like with the duration of no flow, the ratio of precipitation to potential evapotranspiration from the preceding year is the most influential predictor, followed by the ratio of precipitation to potential evapotranspiration at the end of the preceding climate year, followed by a number of other variables related to either precipitation or potential evapotranspiration. So we can really see here that the climatic water balance from the year before the year of interest is driving the timing of no flow within the year. And yeah, to kind of put that another way, the antecedent climate conditions are really critical for predicting the onset of no flow conditions, as well as its overall duration. So to sum up that second piece, what are the drivers of variability? What we found is that we're able to provide reasonable predictions of these intermittency signatures using random forest models. The models did best for the duration of no flow, and they had the biggest struggles in predicting the rate of drying. And that kind of points to differences in the driver variables of each of these intermittency signatures. So the duration and the timing, both of which had better predictions, were more strongly influenced by climate, in particular the prior year climate conditions, whereas the dry down rate, which was more challenging to predict, tended to have more kind of nuanced land use and physiographic influences on it. So that wraps up the national scale stuff. And what I'm now going to do is zoom in to a portion of Kansas. This river here, we colloquially call it the Arkansas River, because that's how we say things here in Kansas. And it is quite a large river. It's one of Kansas's 3 navigable waterways. It begins up in the headwaters of Colorado in the Rockies, and eventually makes its way to the Mississippi and out to the Gulf of Mexico. And over much of western Kansas, it flows sometimes, but other times does not. So these two pictures were taken a few years apart, so this wasn't within the same year, but you can see that it's able to sustain flow. It's a very sandy bottomed, highly transmissive substrate for this river that is, yeah, well, when you think of navigable waterways, I guess I typically think of something a bit bigger than that. And that's kind of a reflection of what's happened over the past 70 years in the state of Kansas, which I'll go into next. In Kansas, we've got a great water resource in the western part of the state, the High Plains Aquifer, which is shown as a gray outline in the background here. And what this map shows is Kansas's stream network. The lines that are red are streams that between 1961 and 2009 transitioned from perennial to non-perennial. So you can see there's been these very widespread transitions to non-perennial flow across the state. Our specific field site that I'm focusing on is right around here. So it's towards the downstream end of this non-perennial zone, very close to where it becomes perennial again. And these are driven by irrigation in the High Plains Aquifer, causing stream flow depletion. And this is very well exampled, well typified by a comparison of 2 gauges, one of which is the Coolidge gauge here. It's just over the border with Colorado. Colorado is required through an interstate compact to provide a specific amount of water to the state of Kansas each year. So the amount of inflows to the state have been relatively constant through time. And then if you look downstream to Dodge City, after you go past quite a bit of extensive irrigation, you can see that up through the 1970s, there was fairly good agreement between the water flowing into the state and the water that made it to Dodge City. And once you get to the mid 70s, it kind of falls off the cliff, and you see very widespread no flow and persistent no flow conditions until eventually they decommissioned the gauge because there was no flow there, which speaks to the challenge of long-term gauging on non-perennial systems. So at this specific site, we wanted to investigate how has stream intermittency varied historically, what causes shifts between wet and dry or flowing and non-flowing conditions, and then what's the role of heterogeneity in the subsurface in influencing these stream aquifer interactions. So we run an internship program here at KGS, and one of last summer's interns is Kyle Compare. He's currently a PhD student at Florida State University, so you may cross paths with him someday, but he was doing a lot of the work that I'll be sharing here, as well as collaborator Aaron Siebold at KGS and Qi Zhang, who was at KU and has since moved to the University of Vienna. So taking a top-down look at this field site, this is about where those pictures I was showing were taken. So just south of this bridge, the water flows from south to north in this picture. And you can see there's a pretty narrow riparian corridor, which is surrounded by agriculture, much of it irrigated, though these two particular fields are not. The Kansas Geological Survey has been collecting data here for about 20 years, and through that, we've developed a conceptual model of the subsurface here. So immediately kind of underneath the stream and the sand that you can see there is the unconsolidated alluvial aquifer. So this is a pretty coarse sand and gravel with silt and clay inclusions in it. It's very transmissive. Water flows into it about as quickly as you can pour it on from a bucket. So it really can absorb the water quite quickly, and water can move through it quite quickly. That's underlain by a very low permeability clay. There's some evidence that that low permeability clay is leaky, either through kind of pinching out in some locations and are being fractured. I'll talk a bit more about that later on. And then underneath that is the High Plains Aquifer, and that's the location where a lot of that pumping has occurred. So you recall I mentioned earlier that pumping has driven these large-scale shifts from perennial to non-perennial streams in western Kansas. And this site's interesting because the pumping is not in the sedimentary unit that's directly interacting with the stream. So we've got kind of this barrier between the pumping and the stream. So it's an interesting site to investigate some of these more confusing and confounding stream aquifer interactions with pumping. So looking at this specific site, these plots are a bit like the ones I was showing earlier, but the y-axis on this top plot is daily discharge through time. It's log scaled because there's quite a bit of flow variability here. Since the start of the record in 1998 up through the end of 2020. And everywhere that's shaded yellow in here is a time when there was no flow at this site. So you can see there's a couple periods where that happens. The second plot beneath this is just taking the annual data and just stating what percentage of the year is the stream dry. And what we can see, so there's really two primary regimes at this site. We've got flow that's either on or off, and we can kind of denote these, and I'll refer to them as sort of wet regimes and dry regimes, where we go from wet regime where there's very consistent and long-term flow over the course of years, to a dry regime where we've got 4 years with maybe 5% of days that have flow, back to a wet regime where it's flowing pretty much the whole time, back to a dry regime, and then towards the end, the past 5 or so years have been a bit different. We've got more of a transitional period where we're more gradually going from dry to wet. So if we just look at kind of describing the flow regime and the intermittency regime at this site, well, we can break it out in a few ways. This plot's showing the histogram of or a bar plot of the duration of no-flow events at this site, ranging from no-flow events that are less than a week in length to no-flow events that exceed a year in length. And what we can see is that while the majority of the dry periods are pretty short, there's a few long periods that dominate the historical record. So those are those long yellow bars that I was showing on the preceding slide. The no-flow events that are greater than 365 days in length make up over half of the total no-flow days, despite being a very small number. And those no-flow events that are long tend to start in the summer. So this is once again a bar plot showing the number of events for the onset of no-flow by the seasons, working at winter, spring, summer, and fall here, with the intensity of red in this plot indicating the mean event duration during that season for events starting in that season. So we can see that we get a lot of events that start in the summer, and they tend to be very long. Summer is also when people grow crops in this area, so that naturally made us think, what's kind of the connection between the stream and the aquifer in this setting? So first we dug into the climate piece of the puzzle. So these plots are showing, the bottom plot is that same discharge plot I showed previously. So once again, yellow is shaded when there's no fall. The top two plots are both showing a climatic index called the SPEI, or the Standardized Precipitation Evapotranspiration Index. And I'll first explain what this top one is and then translate it to the second one. So this is the 3-month SPEI. So what that is an indication of is the relative dryness for the past 3 months for a given month. So for example, if we are talking about March 2021, it would be an indication of January, February, and March of 2021 relative to all preceding January, February, and March combinations. And that's just calculated based on the balance between precipitation and potential evapotranspiration at a site. So it gives us kind of a unitless index where negative numbers are drier conditions and positive numbers are wetter conditions. So this 3-month is indicative of sort of the seasonal dryness at the site. And the second plot, the 12-month, is indicative of more the longer term or annual dryness at the site. And what becomes apparent is that our shifts between these wet and dry regimes, which I've highlighted some of them with circles on this plot, are accompanied by large departures in that 12-month SPEI. So it takes, a beyond seasonal accumulation of water deficit or water surplus to kind of shift back to that flowing condition. Whereas shorter term variability, for example, the most extreme dry event in this record, or about equal to the most extreme dry event in this record, in 3 months did not cause flow to cease. So it takes the longer term accumulations of either water excess or water deficit to drive shift between these regimes. And the seasonal impacts are really the most evident when you get into the transitional periods between a dry regime and a wet regime. There you can really see some kind of bouncing around in the 3-month SPEI that's associated with the cessation and onset of flow. If we then look at the data we have at the site, some of the field-specific hydrologic data, what's shown here is a plot of the elevation of water level in 3 different water stores. So we've got in green is the water levels in the river. Whenever that kind of flat lines, that's actually indicating that the water levels drop below the stream bed and it's totally dry. So the river water level here, the alluvial aquifer water level is shown in this pinkish color here. And then the blue water level is showing the high plains aquifer. And then you can see in this one, very clear signal of seasonal pumping where the water level declines and then goes back up. And we can, once again, annotate those with the same regimes that I've been talking about earlier to look at how these vary depending on the flow status. And what we can see is that there's a very strong agreement between the wet and dry regimes and the water levels in the alluvial aquifer. So when you've got the water levels in the alluvial aquifer falling far below the stream bed, you have no flow conditions except in the rare condition where there may be a precipitation event that triggers a brief flow. And in order to sustain flow, you really need that water level in the alluvial aquifer to rise at or above the water level in the stream bed. So that's a very strong storage-driven picture of the flow regime. We do get some occasional ephemeral flow in response to precipitation when the water levels in the aquifer are low, but it's very brief, just on the order of a few days or maybe a week or two. So with this flashy response to precipitation, what you need in order to kind of transition between these regimes is basically multiple precipitation events that are triggering recharge in this alluvial aquifer. That recharge will then kind of quickly dissipate laterally as the water level goes down. And as you get that flashy aquifer response to precipitation, if you get multiple events, eventually it'll push water levels up above that stream bed elevation, triggering the ability for that stream to sustain flow through time. So if we look at that then in terms of the cross section I showed earlier, if we imagine water levels in the alluvial aquifer, as shown by this blue line, the climatic water balance, so precipitation and potential ET, control the water that is input or output to and from the aquifer. As there's long dry periods, that drains the tub of that alluvial aquifer, which can then trigger a transition to a dry regime. And you need long wet periods in order to refill that tub of the alluvial aquifer and go back to a wet regime. The short-term weather tends to be the most important when water levels in the alluvial aquifer are very close to the bottom of the stream bed, because it can very quickly kind of jump back and forth across that boundary. And this leaky confining layer is still question marks to us. So it's not clear exactly how that is interacting with the alluvial aquifer, but it is quite clear that as pumping occurs in the high plains aquifer, leading to a drawdown of water levels in that high plains aquifer, we're seeing a corresponding decline in water levels in the alluvial aquifer. So what we're going to be focusing on this summer is trying to better characterize both the fluxes of water across this leaky confining layer, both to understand the depletion of the alluvial aquifer, as well as to understand recharge of the underlying high plains aquifer. So to sum up this piece of the puzzle, what we found is that historically at this site, there's been some transitions between dry regimes and wet regimes over time. Base flow makes up the majority of total discharge here. And these shifts tend to be driven by the annual scale water deficit, so the difference between precipitation and PET. And what this is pointing to is a storage-driven flow regime at this site, where we really need to fill up the alluvial aquifer before flow can be sustained at this site. And the subsurface piece of the puzzle is still a work in progress, but our hypothesis is that there's lagged effects on alluvial aquifer water levels from pumping in the high plains. So what that would point to is that we've got both these kind of climate-driven and pumping-driven lags sort of interacting with each other at long-term timescales. So we've talked about the country, we've talked about a specific reach. So some of the lessons we can kind of synthesize from these two different scales we've looked at is that there can be very long year or more time lags associated with flow in these non-perennial systems, which differs a bit from, I would say, a common perception of intermittent streams, which is that they flow when it rains. Here we can really say, our evidence is pointing to the fact that they flow when it rains and when it's been raining for a while, if you want flow to persist. Second, the physiographic characteristics. So, at the national scale, this is things like watershed area, bedrock depth. At our reach scale site, this is things like the alluvial aquifer and the potential leaky confining layer, provide a template that forms the basis for interactions between climate and human activities. And the time scales over which those interactions may occur, we believe is going to be a function of those physiographic characteristics. And a third point is that in order to understand this stuff and beyond just a single site, we really need to improve the monitoring network of non-perennial streams. I showed that map at the beginning, saying that there's many large white patches on the map without a single long-term non-perennial stream gauge. And what I believe this analysis kind of points to is the importance of also considering subsurface monitoring at many of these sites. So with that, I'll just throw up a picture of the Arkansas River, and I'd be happy to take any questions.
Great, thanks so much, Sam. I don't know if you noticed me scrambling a little bit there. We lost the YouTube stream in the middle, but we relaunched it. We had to do it with a new address. So your adoring fans might have to stitch together the two versions, but we will certainly upload the full recording that we have here from the Zoom to the YouTube. So sorry about everyone out there. Hopefully you're back on the YouTube channel now. We'll take questions from YouTube as they come in, but I'll open it up first to the room here, to the Zoom room. And I'll always like to prime the pump a little bit here. I've got a couple of questions for you. I'll start with a kind of an easy one first, like method-wise. For the first analysis you showed, the sort of nationwide analysis, and you had the hydrograph cartoon where you have this like dry period that is continuous. So just like, so simply did like, if you had a dry day in March, a dry day in June, a dry day in September, did you add those up or did they have to be continuous? And it seems like you know, very different types of sort of watershed processes that would drive a continuous drying versus an intermittent drying.
Yeah, that is a really good question. So for that one, we were looking at, for our 3 signatures, for the duration, we added up the total number of dry days within the year. For the timing, we took when the first one happened within the year. And then for the dry down rate, we took the average of all of the local peaks to the dry conditions. So I guess you could say we sort of treated the 3 different signatures a little bit differently with respect to those. And yeah, at one point we were thinking about including the number of sort of discrete dry events as one of the pieces we were putting into this analysis, but it was sort of washed out by a lot of 1s and 2s in there. So while there were some very interesting kind of outliers on that extreme that really went back and forth from flowing to non-flowing a lot, yeah, in the end it didn't make the cut. But I think as we see here in Kansas, that sort of dynamic variability can be quite instructive about what's happening in the subsurface.
Yeah, your transitional period, like at the end of that, for the second part of the presentation was like, yeah, you'd have many, 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 right? And so think about duration, frequency, timing, rate of change, and can't remember the fifth magnitude, right? So those are all kind of interesting elements. I see we got Frederick Chang on here because he knows the secret Zoom link because he got kicked off the YouTube and came in. Good to see you. AJ, you got a question for Sam?
Yeah, it's kind of building off of what you were asking, David, but I think the reach scale data is pretty clear that there's less water moving through in a given year, and that's dry, and it's down in the aquifer. The aquifer's being drawn down. But at the national scale, did you look at the peak annual flow or cumulative annual flows and how those are changing over time? So is it there's less water moving through these drying out streams, or is the same amount of water being concentrated in a shorter time period within a year?
Yeah. So I'll say we didn't specifically look at that, but there have been some sort of regional to continental scale studies about stream flow trends that have found, looking at perennial streams, kind of similar dynamics to what we're seeing here, with drying in the south and the west, wetting in the north. So yeah, I would be curious to know whether the trends in duration of no flow, for instance, are also reflected in a trend of the total magnitude or just the peak magnitude, because there may be some interesting dynamics at play associated with the intensification of the hydrologic cycle and how that comes into play.
Yeah, I think it's probably a lot of different hydro regime metrics that are collinear or correlated, but like, do the dry days, right, total mean flow, peak flow, all these things, like you unpack that a little bit in the first, because you have these 3 metrics driven by 3 different sort of scale, physiographic, climate. So I think yeah, looking at the high side flow indicators as potentially, or like first hypothesis would be, co-varying, right? Negative,
Mhm.
negative reductions in those as well. So yeah, it's an interesting question, AJ. All right, we got no questions over from YouTube yet because they're feeling a little bit shy. So I'll come back with another one. What you presented is climate data, flow data, some aquifer data. So I guess two questions, like how do the inferences that you're drawing about the hydroclimatic system, how do you or your collaborators or colleagues, do you use models along with these data? And then also hydrochemistry, or so like, if you're looking for sources of water from a shallow versus a deep aquifer, have you started to puzzle that out either with a modeling approach or with some chemical analysis like source tracking, things like that? Oh, there's his 30 every half an hour he gets the frozen, right? Okay, you're back.
I'm back now. Yeah,
Did you get the
so
question?
yes, I heard the question. So thanks. Yeah, so I guess first piece is kind of methodological. So what we're doing now is I do a lot of modeling, a lot of kind of numerical modeling. I'd say that's one of the things I've been trained on. For this system, I'm not thinking about developing kind of a full numerical model of it. Because I don't know, I've just recently been tending towards more parsimonious approaches to answering these as opposed to those highly parameterized models. But what I am doing is, there's an interesting approach called transfer function noise modeling, where you kind of have characteristic responses of an aquifer to different stresses or stimuli, like stream flow water levels or pumping or something like that. So that's sort of the next step, is trying to use this sort of transfer function approach to figure out if that can give us some insight into the time lags between changes in water levels in the High Plains aquifer, the response of the alluvial aquifer, and kind of vice versa, if we do think we've got some bidirectional flow over there. The hydrochemistry piece is, I think, quite interesting, and that's one where we just ordered a bunch of sensors and we're going to put them out this summer. So we've got, I think, 12 different sort of floodplain, alluvial aquifer, and high plains aquifer wells that we're going to be getting conductivity data in, and hopefully kind of try to develop some rating curves to relate that to things like TDS, do some grab samples of nitrates, and that's work that Aaron Siebold, my collaborator here at KGS, is going to be taking the lead on. But yeah, I think the chemistry aspect of it's going to be very illuminating, especially for some of these more indirect or counterintuitive flow paths.
Yeah, great, thanks. We do have a question from Saeed Mana. He asks, what are the plans to investigate the role of confining leaky layer in Arkansas? Pumping tests, groundwater level fluctuations, or others? So how are you going to figure this out?
Cool, great question, Saeed, and hopefully you can come help us out with this problem. Saeed and I have been emailing recently, and yeah, we've got a few angles. So there's been some historic pumping tests collected at this site. There's a number of sort of well logs from the installation of those wells that I just mentioned. So piecing those together, we've got, if not a complete, but a spotty picture of what the leaky confining layer looks like. And I think the fruitful angles that we might want to pursue are some of these geochemical methods, looking at transfer functions to figure out the time lags of exchange, but also looking at whether there's critical stage thresholds or alluvial aquifer water level thresholds that would trigger recharge into that high plains aquifer, because you do have, it's not the picture I drew that leaky confining layer was perfectly flat, but it's very heterogeneous. And there's some evidence to indicate that when you get very large overbank flooding, that's when you can really kind of activate some pathways that get down into that deeper alluvial aquifer. So I think that's another piece that we're hoping to do. Potentially, depending on how COVID-related travel plays out this summer, we're hoping to do some cross borehole geophysical investigations to also try to get subsurface picture of what's happening between the wells where we have data.
Great, thanks. Well, that actually answers a question from Anastasia about if you're planning to use geophysical methods. So the answer is yes, hopefully.
The answer is yes, yeah, and we tried it with electrical resistivity last summer, kind of right along this sandbar, but we weren't able to penetrate deep enough to get to that confining layer. So we're moving to the cross borehole techniques and seeing if that gives us any answers.
And then we have a question from Fred. It says, awesome talk. I think he doesn't have a microphone, even though he's in here. He might have missed it, but did you get a chance to check for regional differences across the US on the strongest controls for the various metrics? So you broke out by region, sort of like the different responses, but I was scrambling too, so I might have missed it. Do we know if there's a regional sort of variation in which controls were, which of the random forest drivers were strongest to each of the metrics?
Yeah, that is a good question, and one that it's within my capabilities to answer, but I don't know right now. We did, so I made national scale random forest models, which is what I shared with you, and I also made a separate random forest model for each of those 6 subregions and each of those 3 intermittency signatures. So another kind of 18 models are on my computer. We found that the performance on the test data and training data was very similar, whether I used the single national model or the 6 regional submodels. So we focused on the national model and haven't dug into what are the different regional drivers. But I'm very, it's quite easy to imagine that some very different and useful insights could be gained by looking at those regional models. So that is maybe putting it back on my to-do list. Thanks for the question.
Awesome. Well, yeah, thanks, Fred. And thank you very much. Oh, AJ, one more. Go ahead.
Sorry. Yeah, sorry. I know it's kind of running over time a little bit, but the chemistry side and what it sounds like Aaron Siebold is going to be looking into is really interesting. If I think about where the Arkansas and other rivers draining the agricultural Midwest are eventually flowing into, right? They're going into the Gulf of Mexico and delivering all of these nitrate and phosphate subsidies that are fueling the algal blooms. If these rivers are drying and the water isn't flowing, those contaminants are going into the ground, into the aquifer. So have you or anyone considered potential implications for like Mississippi River Basin nutrient load reductions driven by drying of streams?
Yeah, that is quite a question that I've encountered before, and a really interesting one. I think I'll raise 2 points. So first is that we are seeing long-term increases in nitrate concentrations in the aquifers in this area. So there is definitely nitrate kind of making its way into the groundwater. As far as the Gulf goes, just in terms of sort of the volumetric discharge from this river, it's the proverbial drop in the bucket compared to systems like the Missouri or something like that. So in this specific case, sort of that drying might not have that effect. But if you think about, this is a 7th order stream, so it's pretty big. If you think about distributed across the Midwest and the upper Midwest, all of those headwater streams that are potentially changing their drying regime, changing their freezing regime, in that case, I think shifts in perennial versus non-perennial could have quite a large impact.
Great. Thank you, Sam. Thank you so much for joining us today. And thanks to everyone out there on YouTube. Sorry for that hiccup. We don't know what it was. But if you will join us next week, we have Dr. Lauren Koenig. She's a postdoc at University of Connecticut. She's going to be talking, or talk is called Taking the Pulse of River Ecosystems from Stream Reaches to Watersheds, a topic we like to talk a lot about here in the W3 seminar. Thanks, folks. Very nice to meet you, Sam. And thanks all for coming. Have a great rest of your week.
All right.